Hi, and welcome back to the channel. About a month ago, I put a video out on Top2Vec, and it was pretty well received. That video was really just a cursory overview of the library, why it's useful, what it's good for, and why it's probably one of the better topic modeling libraries out there in Python. In this video, we're going to be kind of starting a much larger series on Top2Vec. It was very clear from the comments that you all wanted to see more information on Top2Vec and some of the parameters that you can pass to it during the training process, and some of the more complex things that you can do with it when you actually start applying the model. And we're going to be doing all this over the course of several videos in which we talk about Top2Vec in a lot more granular detail. Over the first 5 or so, we're going to be covering the different parameters that you can pass to the Top2Vec model during the training process. And there are a lot of parameters that you can pass to it. Then we're going to switch over and start talking about some of the more granular things that you can actually do with the Top2Vec model. And finally, we're going to see all this come together in the final video of this series, where we build a Streamlit app designed around Top2Vec. And kind of some of the good practices in app design, while also explaining some of the more advanced things you can do with Top2Vec in production. All of this will give you not only a good sense about Top2Vec as a library and really kind of exploring the class Top2Vec as a whole, but it will also give you a good sense about app design and how to take something like a topic model from Top2Vec and apply it in production to actually solve some kind of real-world problem. And we're going to be doing this with the Bitter Allo project's dataset called Volume 7 from the Truth and Reconciliation Commission. It makes for a great case study because the data in there is highly clusterable, because a lot of the material in there is highly structured in language, meaning that there are going to be a lot of words that overlap between these different documents discussed. And if you want more information about that data set, check out the first video on Top2Vec where we used it and talked about it in more depth. In this video, we're going to be focused on the training process, and we're specifically going to focus on what parameters we're going to be discussing in this series, and then we're going to switch tacks and start talking about really kind of 2 parameters in depth. We're going to be looking closely at the speed parameter, and in Top2Vec there are 3 different arguments you can pass to that. There is fast learn, learn, and deep learn. We're going to see the advantages and disadvantages of each of those, and then we're going to also take a look at another parameter called workers and explain how workers works and why you might want to use it during the training process, if at all. And then that's going to set us up for the next few videos to explore the parameters in a bit more depth. Some of the ones that are going to have a much larger impact on the model as a whole, and maybe ones you want to consider based on how you want to use the model in production. So let's pop on over to Jupyter Lab and just jump right in. Now that we're in Jupyter Lab, let's go ahead and just jump right in. So the first thing that I need to do is I need to import my data set, and this is going to be stored as a pandas data frame. And so let's go ahead and import pandas as PD. And if you're not familiar with pandas, I have a whole series really and textbook on this channel for working with pandas. We're also going to be importing regular expressions to clean up our data a little bit more than we did in our introductory video on Top2Vec. And this is going to allow us both to load the data and actually clean it. The final thing that we're going to be needing is from Top2Vec, import Top2Vec. And if you follow my initial video, it walks you through all the installation processes for the Top2Vec library to get it up and running on Windows or Linux. As I understand it, there are some problems with running this on the new Mac M1. Nevertheless, it should work for you just fine. I have misspelled Top2Vec, there we go. And now everything should load up smoothly. Once we've imported everything, now comes the time to actually load up our data. And so let's go ahead and look in our directory. Again, this is on GitHub for you. We'll notice that vol7.json, again, this is some of the data that we've been cultivating at the Bitter Allo project around the Truth and Reconciliation Commission of Apartheid South Africa. So let's load up this data set by making a df variable, and this is going to point to pandas underscore read JSON data vol all lowercase 7.json. And let's take a quick look at it. And as you can see, we've got names in one column here and descriptions in the other. Now, because I'm going to be making this video for people who are not familiar with pandas syntax necessarily, let's go ahead and just kind of convert the descriptions section to an object. We're going to call this docs, just like we did in the first video, and we're going to work with it as a list. So we're going to say to list, and let's take a look at docs and print one of these off so you can kind of see what it looks like. So this is really useful. We have some information that we want to clean up. Let's take a look specifically at docs 100. I went ahead and I found an example of this. You'll notice that within our data we've got these parentheticals where we see things that might be explanatory for a reader, but might throw off some kind of topic modeling approach. What these are case numbers, and it tells us where we can find information that's contained in this description in the actual testimonies themselves in the amnesty records. But these aren't really useful for topic modeling. What'll happen is descriptions that contain this kind of sequential data, the numbers will be dropped off, but the AC will remain. They will be clustered closer together, despite the fact that they don't have a lot going on semantically similar within the description. So one of the things that we want to do is we want to clean these things up just a little bit. And the other thing that we want to clean up is that in some instances there'll be a case where the description says see Trojan horse attack or something like that. And so we're going to clean up both of these in a couple different steps. So the first thing that we're going to do is we're going to say docs is equal to d.replace, and we're going to just use some list concatenation here just because it's a little easier to do. All we're doing is we're replacing any instance of C followed by an open space, which is an example of these things we want to clean up, and we're going to replace it across all of these items. The next thing that we're going to do is we're going to be cleaning this up as well by replacing anything that is found in a parentheses. And this will also get rid of parentheticals like this, which clarify acronyms. So like in parentheses OFS for Orange Free State. And the way we can do this is we can use regular expressions. And again, I have videos on this channel that talk about regular expressions in more depth. But all you need to know is that what you're about to see is an expression that will allow for us to, and actually I'm just going to copy and paste it over because it'll be a little easier. It allows for us to isolate instances where there is a parenthesis and remove the parentheses and also remove the contents found within that parentheses. And so we're going to replace it with nothing, and we're going to do this to D, and then also we're going to go ahead and clean them up a little further and get rid of instances where there is a space period and just put a space there. And we're going to do this for D and docs. And if you don't understand the Python syntax here, that's okay. I don't really cover a lot of this in my videos. I probably should do a video on it in the near future, but let me just demonstrate the results for you so you can kind of see what it does. Notice right here, we've got this AC2000, these case numbers. They are now removed. And we've officially kind of done some pre-processing on our documents. So this is going to be what we work with in this video. There's about 22,000 of these descriptions. And what we want to do is we want to model them, and we know that they're going to be modeled easily and well because they are highly structured in their language. And that makes it easier to kind of cluster them more reliably. And so let's take a look at some of the more advanced things that we can do with Top2Vec. We can do that by printing off Top2Vec dot underscore underscore doc underscore underscore. And what this does is this prints off for us the doc string or the document string at the top of our class. You can also use the help function, which will give you everything, including the different methods that are available. But for this video, we're only interested in what the class parameters are, because these are going to be the things that we focus on. So the first thing that we actually see that we actually need are the list of documents. Now we saw this in the initial video. The next thing that we can pass to the Top2Vec class is min count. We're going to be working with this a little bit. Essentially what min count allows for you to do is to adjust the number of times a word must appear across all of your documents in order for it to be considered a word worthy of modeling. So if you set this value to 1, you're going to be considering every single word. Now this is not always a good thing to do. However, it's very good to do when you're working with, and they tell you right here, for smaller corpora. So if you have maybe only 100 documents, you're going to want to lower this threshold to probably somewhere in the range of in the single digits, maybe 5 to 10 even. If you're working with larger documents like we are, a larger quantity of them, a default value of 50 is perfectly fine. And we're going to play around with these values a little bit and kind of take a look at some of the results in this video and in the videos that come after. The next thing that we can pass is n-gram vocab. I'm not going to focus on that too much right now, and I will be talking about it in just a second, but this is essentially going to be one of the core things that we talk about in this video. N-gram vocab is the way in which you can kind of set the parameters of Top2Vec to include bigrams, trigrams, etc., to include phrases or multi-word tokens, things that aren't just one word. And this is really useful for things like right here, Orange Free State. We want our model to understand that Orange Free State is in fact its own self-contained entity. And these are the kind of the useful ways or useful things you can do with n-gram here. Also, you would want to model your Top2Vec model to understand that SAP members is a specific kind of token that is very specific to what how a person relates to the organization of SAP, which is South African Police. And we're going to be talking about that a lot more in this video. And this is all done via Gensum, so you can pass in some keyword arguments here. The embedding model that we can pass to Top2Vec. Now, this is a little bit more complex. What you can do here is you can choose and select the way in which you want to generate the document in word embeddings. And so this is going to be how you vectorize essentially your different texts, which is going to be how your Top2Vec model will actually be able to cluster them based on semantic similarity at the vector level. Now, Top2Vec, it goes through and explains kind of some good stuff about when to use certain encoding models over others. If you're using really kind of niche vocabulary, a very domain-specific set of words. Maybe you're in the medical industry, maybe you're in, like we are right here with South African dialect of English. You might want to opt for Top2Vec because it's going to train this for you. The other things that you can do is you can use some off-the-shelf models here, and these are going to be really useful when we get to later videos when we start talking about multilingual Top2Vec. Again, this comes up with some of my data that I work with at the Holocaust Museum in DC that have oral testimonies in English, German, and sometimes a segment of an oral testimony that will switch between the two. So if you know your documents are going to be multilingual, you'll want to consider that. And again, for each of these models, you've got a large model and you've got a regular sized model. Large is going to give you a better vector representation of your texts. It'll take a little bit more time to actually do, though. And so these are going to be the main things that we focus on in this video. Again, in later videos on Top2Vec, I'm going to be covering a lot of these other parameters in much more detail. But for now, let's go ahead and actually just one more thing to cover, and that is speed, which we're going to see in this video. The speed parameter allows for you to determine how quickly and how deeply your Top2Vec model represents your texts. So if you used fast learn, you're going to have the fastest training time, but you're not going to necessarily have the best clusters. Likewise, if you use learn, you're going to have this kind of neutral area between a good representation of your documents and the vectors, while at the same time being a little quick in speed. And finally, we have deep learn. Deep learn is going to produce the best vector representation of your texts and the clusters that you get from them, and it's also going to take a lot longer to train. Now, I would use deep learn if, as we're going to see in this video, I wanted to produce a Top2Vec model that I would expect to use in production in some capacity. I would use fast learn if I were trying to do some quick tests to see if the documents at hand really have the potential to be modeled. Do we see similarity across all of them? This can be used in lieu of a traditional TF-IDF and k-means cluster approach, which I have a video for on this channel. Learn is something that I would do if I wanted to have a bit more of a structured test when I'm just kind of experimenting with my documents. But I want to see if I give it a little bit more time, if the documents will cluster a little bit better, or the vectors will be a little deeper to actually cluster the documents more effectively. So these are kind of some of the main parameters that we're going to use. As we're going to see when we start trying to develop something for production, we're going to be using document IDs. The final thing I should probably mention, one last thing, I know I've said this a few times, is workers. A good way to think about workers is the amount of essentially the percentage of your CPU that you want to dedicate to the training process. You'll need to figure out how many workers are available to you with your CPU. On this laptop, I've got 16 available. I'm going to set the workers to 8, however, and that's going to be so that I can use multi-threading, which will train my models a little faster for me, but we're not going to be watching the training in real time. And these final bits down here, we're not going to worry too much about in the series. They're a bit beyond the scope. Essentially, it comes down to the way in which you want to use UMAP, which is going to be how you, or HDB scan, which are going to be ways you do dimensionality reduction. We're not going to be worrying about those right now. And I'm going to be ignoring verbose, which just gives you more updates on how your model's doing during the entire training process. So all of that said, let's go ahead and start seeing how these actually work in real time, or in with real examples. And so the first thing that I'm going to be doing is I'm going to be using just our off-the-shelf basic thing that we saw in the last video. I'm going to redo it for this one, and I'm going to kind of pop back once it's all done. We're going to just pass in our documents, and we're going to go with a speed that's going to be equal to fast learn. So we're going to try to do this very quickly and very effectively. And we're going to just go ahead and do that, hit execute. We're going to pop back when this is all done. And we're back. We see that our fast learn approach trained our model in really only about a minute. That's pretty good with 22,000 documents. Let's go ahead and take a look at the speed it would take to actually train a model with just the learn parameter. I'm going to go ahead and switch this and call this model learn. And we're going to go ahead and run that. And again, I'm going to pause the video here, and we're going to compare the time to finally the deep learn. And then we're going to compare the results with each of these models. And as we can see here, our learn approach was really kind of a very comparable time. We have about just under 1 minute to do that. Let's go ahead and do a deep learn, and then we're going to kind of compare all these models to see where they actually are different. And for this, I'm going to call this D-learn, so we can kind of keep them distinct. Let's go ahead and execute that, and we'll pop back once again when all of this is done. And now we're back, and we can tell that the deep learn approach has taken a significantly longer time. With 22,000 short descriptions, they're roughly between 2 and 3 sentences apiece. We're seeing something around 5 minutes on the same computer. So this is without any actual workers going for us. And let's go ahead and test out to see how much more quickly we can get this task done if we actually assign workers. I'm going to just simply rerun this entire cell with workers set to, let's set it to 14. I believe I have 16 available, and this should run significantly faster for us. We're going to go ahead and execute this cell, and we'll pop back when everything is done once again. And we're back, and we actually have managed to somehow slow down the training process, which I'm not entirely certain of how we managed to achieve that. Yet nevertheless, these are the results. Now, what I want to do for the remainder of this video is kind of take a look at what these models look like, how they are a little bit different in their the size of the topics that they represent and the numbers of the topics that they represent. So to do that, we can go ahead and work with what we've already seen in a previous video. And so I'm going to copy and paste that code over. What we can use is we can use model.getTopicSizes to get two pieces of information. We can get the essentially the topic sizes, which will print off the size of our each individual cluster, and then we'll get the index for each individual cluster. So as we can see, we actually have 51 different topics in our Top2Vec model with our small model. Now this to me is quite surprising. This is very, very bad. I know for a fact that we do have a much more broader diversity of topics. And in fact, if we go ahead and we look at our model_learn, not our quick model, we'll see that we actually get that representation a bit more broadly. We actually have now at this stage 286 different clusters. And if we go ahead, or topics, and if we go ahead and we do this again, and we do it with model D-learn, we'll see that that number gets honed down a little bit to 271. So this is what we're able to see here. with the difference in document sizes with each model. But let's take a look and kind of take a look at one of these topics to kind of get a sense of how it might actually differ semantically. So let's pick, remember our Top2Vec clusters go down in descending order. So what I want to do is I want to look at the last cluster here for each of these. So we're going to pick, in this case for the original model, we're going to grab this cluster right here of a size of about 22, which will be 50, and we're going to just kind of go ahead and take a look at each of these. So let's scroll down here and let's print off the words that we actually see, and let me go ahead and make sure that we grab this as well. And we're going to be looking for topic number 50, I believe I said it was. And let's take a look at what words we're actually seeing in these topics. I have grabbed the wrong thing. Let me delete this and copy and paste a different segment over. Here we are. And we're going to look at the topic number 50, so the smallest one. And we're able to see that we have some overlap here that looks somewhat consistent. Both of these individuals were at the exact same event. One is likely male because we don't see a pronoun used here, which is oftentimes the case. And here we actually see she to reference that the individual is in fact a woman. If we go down the list, these clusters don't look bad. What has me most concerned, though, with these, with Model 1, the fast model, is the fact that we have such large clusters for so few actual distinct topics. That's a good indication that the model hasn't actually achieved really a good sense of what separates these larger clusters out in a more nuanced way. So let's go ahead and do this exact same problem, or exact same task, with another model, specifically our second one. Let's go ahead and copy all this over, scroll on down, and we're going to take a look at model_learn. And in our case, we are going to grab topic number, I believe it's 286, which is the last one. And we're able to see again that this model is clustering things very well. These again have a high degree of overlap, and we're not expecting to see in the last cluster the exact same documents from each model. They're going to cluster things a little differently. And again, we can go ahead, and I'm just providing this for you in the repository so you can kind of go ahead and compare these in a bit more depth. I believe 277 was the last cluster from that one. Maybe it was 276. I have to scroll back up and just take a look real fast. The last one's 271. So let's scroll back down. And we'll print off topic 271. And again, we're able to see that there is significant overlap in these documents. It looks likewise what we saw with Model 1 and Model 2, that the degree of overlap is significant because these individuals experience the exact same event, and so the top 10 are actually ones that are nearly identical. This is what we'd expect to see. Again, this is highly structured descriptions, and we've been able to find them across this vast data set, despite the fact that they're removed in the data set, which is listed by name, quite far apart. So that's a good little indication of the difference in not only time it takes to train a model, but the differences you can expect from the quantity of clusters that you see and the quality of those clusters. Again, it would require a much longer video and hours of going through and kind of exploring each of these on my own to really get a better sense of these distinctions, but I'm including all this here so that you, if you are interested, can go through, recreate the code here, recreate these examples, and go ahead and explore these in more depth yourself. That's where I'm going to wrap up this video. In the next video, we're going to do the same thing, but we're going to take a look at something a little bit more important, and that's the distinctions, not only in the training process, but in the development of n-grams, so representing those multi-word tokens. And we're going to take a look at some of the hyperparameters that we can pass to n-gram in the Top2Vec library. That's going to be it for this video. Thank you so much for listening. If you've enjoyed it, please like and subscribe down below. As always, I do everything on this channel for free. I try to take all the money that is given to this channel and put it back into the channel. And thank you so much to all the Patreon supporters who help keep that all possible and help keep all this content free for everyone. If you get a lot out of this channel, please do consider supporting it via Patreon or become a YouTube member down below.